Hey guys, this is Josh Myers, and I know I said in the last video that I was going to be done for the night, but I was just so giddy to start the hybridization portion of this channel that I just wanted to go right ahead with it. So I'm Josh Myers, and on behalf of Academia on Demand, I'm introducing you to the idea of hybridization bonding theory. Hybridization bonding theory. And so, using the Vesper and Lewis theories in the last video, we have been talking about drawing molecular structures in terms of sort of what I would like to call a pool of electrons. A pool of electrons. And what I mean by this is when we are drawing our Lewis structures from previous videos, what we are doing is we are taking, say, the molecule CO2. And we are saying, okay, well, CO2 has 16 valence electrons. 16 valence electrons, and so somehow using these 16 valence electrons, we have to get a molecular structure that creates energetic stability for all parties. And so we can arrange these 16 electrons. If we draw this pool, we've got our 16 electrons, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, no, 16. So we've got our electrons, and we say we can pull these any way we want as long as somehow at the end of the day this carbon ends up having 8 electrons in its outermost energy level, and the oxygens have the same idea. However, one thing about hybridization theory is the idea that this theory is more specific. It tells us a little bit more about exactly how these elements bond together in order to create this idea of energetic stability. Because this pool of electrons, this idea where we have electrons and we can put them anywhere we want, this is not accurate to the way elements bond and the way these sorts of exchanges, interactions happen between the atoms themselves. Okay, and so this is why when we do hybridization, it introduces us to the idea of how atomic orbitals become molecular orbitals. So hybridization introduces us to the idea of how atomic orbitals change to become molecular orbitals. So change to I was right just to write about the number 2, which is incorrect, to molecular orbitals in bonding. Molecular orbitals. And specifically, this hybridization theory really overlies the way that this happens, the process by which these atomic orbitals become molecular orbitals. And so before we go into this exact process, the first thing that I wanted to do, besides showing you that this idea of the pool of electrons is wrong, is to show some of the proof as to why from the time of discovering the hybridization theory, the scientists prior to that knew, or at least had questioned, the idea that the Vesper or Lewis theory of molecular structures was wrong. Well, one of the reasons that they knew that it was wrong, besides the idea that it just kind of considered this idea of valence electrons and we would just pool them, as I showed right here in the middle before I erased, there's a lot of evidence that they had to suggest that this theory was wrong. And the first bit of evidence that was very, very strong, it was convincing that clearly there must have been more happening than just simply these electrons filling out outer energy levels and then repulsion and electron pairs and things like that. There must have been more behind exactly what was happening while bonding. And one of the things that scientists looked at was the idea of, if we looked at the Vesper theory and we looked at, say carbon, and we saw carbon, if we say its electron configuration, it is 1s2, 2s2, 2p2, 2p2. And one of the things that scientists would look at when you look at, say, carbon, and carbon can bond to hydrogen 4 times to create methane, in the tetrahedral structure, is the idea that this orbital, if we look at the 2s orbital, it is already completely full. It is already completely full, whereas the 2p sublevel, it is only has two orbitals that are half full, and then an empty orbital remaining. And so what they ask is, how could these single electrons from the hydrogen, if we're looking at hydrogen, this is 2s, that is 2p, and we are looking at hydrogen, which is only a 1s orbital of 1 electron, how could this electron bond to this atomic orbital? How could that possibly happen if this atomic orbital is full, and thus these orbitals could not be occupied by more electrons? How exactly could that happen? And it didn't seem to make sense. And this is exactly why the theory of hybridization was first hypothesized about, was first thought about in a critical manner. And so one of the critical ideas behind hybridization theory is it solves this problem. It solves this problem by promoting an electron. It does this magical promotion, and one of the things that the scientists thought might happen is that this electron may come here and move out of the 2s and move to the empty 2p sublevel, empty 2p orbital, and then there would be 4 half-filled orbitals that could then accept electrons to become molecular orbitals. Because as we can see from the VSEPR, if we're talking about electron pairs, this electron from the hydrogen would bond with this 2s, then another electron would bond with that 2p electron, and they would all bond with half-filled 2p orbitals. And this is exactly actually how hybridization works, as we will come to see. But before we discuss this idea, this solution for how this problem of having a full 2s energy level was solved really highlights the idea of, even though we had a practical model that worked for drawing molecular structures, it seemed to always give us the right answer. For this CH4, we have the carbon structure, but this just shows that science is more than just simply getting the answer. It is understanding why and how and exactly what happens on every step of a reaction or a process. That's why science is so hard. Okay, and now another problem with this theory, even as it is, even if we look at this in terms of hybridization, where this electron is promoted, and we will understand exactly why it does this a little bit later in the video. But another problem with this theory, even if it is promoted and it solves this orbital problem we have here, is the idea that not all of the electrons, so electrons, the bonding electrons are of different energies. So electrons bonding possess different energies. Bonding possess different energies. And the reason why this is a problem is because anytime that bonding occurs, if the bonding is to be stable, if we are to make a situation as we want in bonding, we want things to become more energetically stable, we want this carbon and these hydrogens to gain stability, we get in a situation where if these hydrogens were to bond to the 2s and then to the 3 2p's, not all of the bonds would be of equal energy, because as we know, the 2s is of higher energy than the 2p orbitals, and so therefore when bonding it could not possibly have the same energy, and would thus greatly actually diminish the carbon's energetic stability. So how could this possibly be solved? Because the only way to create this idea of energetic stability, to be able to create this idea in which all of the bonds have the same energy in their molecular orbitals, is to create a situation in which all of the pairs of electrons from their atomic components, all of the atomic components have to be of the same energy. So atomic component orbitals, in fact, component orbitals possess the same energy. This is another portion of this hybridization theory. So, how can this possibly happen? Well, this actually goes hand in hand with the idea of the electron promotion itself. When this electron is promoted to create this empty orbital into half-empty orbital into half-fill this previously empty orbital, what ends up happening is something that only happens in bonding and is not necessarily understood why. And what happens is that these orbitals, this 2s that now has the 1 electron, and this 2p orbital, 2p sublevel that now has 3 electrons, they come together. If we're talking about the Beatles, we came together. Oh yes. Music is just like science, everyone. It's the exact same. Okay. So, let's get rid of that. Okay, so we've got these four orbitals, and we are going to call this new energy orbital, this combination of atomic orbitals, we are going to call it what we say is sp3. And the reason why this molecular orbital, we're going to call actually a hybrid orbital, a combination of the orbitals, hybrid orbital, we are calling it sp3 because it is a combination of an s orbital and 3 2p orbitals. And that is why this sp3 thing, this idea of sp3 bringing the orbitals together, allows us to solve this problem, this difficulty with the energy levels that the electrons bonding are in. So by performing sp3, by performing hybridization, we can almost call this process of transferring the electron and creating a new orbital as hybridization itself, even though the theory is called hybridization, but this is the main hybridizationing process, if you want to use funky words, hybridizationing, by performing the hybridization process. Okay, so that is the hybridization process, and that is how these problems get solved. And so this actually works to a number of advantages for the atoms themselves. It also predicts a lot about how these atoms come to bond with each other. And why they behave in specific ways as they do. And the reason for this, let's keep this up here. The reason for their different behaviors is explained by the way the electrons are promoted in order to create this idea of the hybrid energy level, the hybrid orbital. Let's define hybrid orbital as a combination of molecular orbitals, combination of molecular orbitals that creates a situation in which all orbitals, so combination of atomic orbitals, because we are not bonded yet, they're not molecular orbitals, I'm being silly, atomic orbitals. A combination of atomic orbitals in which all orbitals have the same energy, in which all orbitals have the same energy, have same, writing sideways is so hard, same, in fact, let's write this one over here, we're pushing it a little bit, same energy. And as we know, as we see up here, this hybridization process always involves an electron transfer, an electron promotion, in fact. So always involves electron transfer. Okay. So before we explore exactly how this hybridization often almost characterizes how an element can bond, we are going to compare exactly the energies of the atomic orbitals compared with the energy of the hybrid orbital, so that we can really see how, when we say that a hybrid sublevel, it's actually a hybrid sublevel with hybrid orbitals, how if we create a sublevel of sp3 hybrid orbitals, these orbitals essentially have combined to become these same orbitals. There is no difference in shape. There is no difference in any energy whatsoever. They are literally the exact same orbitals, and this is how they are able to bond and stay stable amongst all the bonding. So if we were to, as we've done before, and we've drawn our box diagrams, draw out our energy arrow. So as we get higher, the energy increases. Energy arrow, we were to look at carbon again. So if we look at carbon, and we were to look at, so say it's 1s orbital, it's filled, 1s, and then we get a bit higher, we get 2s, also filled, if we're just looking at the atom carbon. No bonding taking place, and then we got our 2p up here. Our 2p, and it has 2 electrons. Well, so what we've come to see here, if we're comparing the energies, is that the hybrid orbital is actually, because it is a combination of the electrons, the 2s and 2p, is also a combination or an average almost of the energies of the two. So if we draw our hybrid orbital here, if we're comparing it, we draw our hybrid orbital over here, and we say has four orbitals, and we label it sp3, because for now we are going to assume that sp3 is the only hybrid orbital, even though we will learn differently, but it will have, each orbital will have 1 electron in it. And as we can see, it is of higher energy than the 2s orbital, but of lower energy than the 2p orbital. And so thus, all of these bonding orbitals have the same energy, and therefore energetic stability during bonding is achieved. Okay. So now what we are going to do is we are going to test this idea out with a couple of molecules that we've examined previously in order to see exactly why different molecules bond the way they do, and why they seem to have the characteristic of bonding, of the sort of bonding in which they always seem to behave in a certain way when bonding to other things. And this isn't a coincidence. This is very, very much a science of hybridization. So if we look at the boron trifluoride exception, you're probably, for the past couple of videos, getting a bit frustrated with me. I keep just calling it an exception, not explaining, and now here I am going to explain exactly why boron trifluoride, though boron only has 6 electrons in its outer energy level, it is still stable. I am going to show you exactly why. Boron trifluoride. Okay. And so if we draw out the box diagram for fluorine, because as we know, anytime now that anything is bonded to anything else, and we are just going to, when we look at these problems in terms of hybridization, we are just going to look at the hybridization, the hybrid orbital of the central atoms, So here, if we draw out our second energy level that represents boron, so 2s, and it's filled, and then our 2p, and it's only got one electron in it. And the rest of these are unfilled. Okay, so what ends up happening here is that, as we know, this idea of an electron being promoted to create room for the half-filled orbital here, so that when it combines with these fluorines, so if we draw out the fluorine, hold on for a second, I don't want to lose you here, so if we draw out our fluorine, it's got a 2p, and it's got full, and then half full. And so this half-full orbital is looking to bond with another half-filled orbital of the boron, to, once we erase that, because the electron transfer has occurred, in order to completely fill its orbitals. So here, because 3 half-filled orbitals have been created and there are no other electrons, there are no other stranded electrons in the boron second energy level, boron can only bond to 3 things. Because as we know, in regular bonding, that is bonding that isn't dative bonding, as we saw in the last video, the molecular orbital can only be created. Hold on, let's draw the new hybridized orbital. A molecular orbital can only be created when one electron is donated from one species and one electron is donated from the other species. So here, this represents an sp2 hybridization, because one s orbital has been hybridized and 2 p orbitals have been hybridized to create one sublevel that is of equal energy. So once this has been done, the fluorines can start to bond with these half-filled orbitals in order to create molecular orbitals in which each species has donated 1 electron, just as Vesper theory would say they are electron pairs. And so here, that fluorine would come there, and if there was another fluorine, it would bond with that orbital, and then finally there was another fluorine, it would bond with that one. And that is exactly how this structure comes to be trigonal planar. And the reason why this is stable for boron is because this orbital is completely empty. It is completely empty. So there's no place in which there would be less stability in this state than in a state of 4 bonds. In a state of 4 bonds, the only way to create a molecule of boron in which there are 4 bonds rather than 3 is for it to bond with a negative ion, because that negative ion has to donate what we would say both electrons. That species, that negatively charged species, would have to donate both electrons into this empty orbital in order to create a 4th bond. And that is actually another example of dative bonding. So if there was a fluorine, a negatively charged fluoride ion, and this ion had a lone pair, and because of the idea that boron has the ability to accept another pair of electrons into its empty atomic orbital, and this orbital is actually not part of the hybridization until it is bonded. If this lone pair comes in here and fills this empty orbital, now this orbital becomes hybridized. It becomes hybridized, becomes a part of here, and this would become sp3 if this were to happen because of dative bonding in which both electrons are donated from the negative ion. And so this is exactly how hybridization comes to explain why things bond the way they do, rather than just saying how it happens or what it looks like. And so as we've discussed with boron, one important thing to note is that this characteristic of these orbitals, of this idea of the way boron just set up a orientation, a molecular geometry with the fluorines. This molecular geometry is often characteristic to groups. So this molecular geometry is often, shoot, I need to write with the sharper side. Geometry is characteristic, let's see if I can fit this in, let's just go characteristic of groups. Characteristic of groups. And right here we can actually go right back to the boron example. So if we draw out the box diagram of boron again, we say this is, oh no, I am getting it all over my fingers. Okay, let's try this again. Okay, so we draw out our 2s, and it's got the 2 electrons, and then we draw out our 2p, and it's got 3 orbitals, 1 electron. We promote that electron, as in hybridization. This hybridization, as we know, only happens when bonding is a possibility, when almost as though molecules know that bonding is a possibility for it here and that it can gain greater stability. The laws of physics say it can do this. Okay, so this is boron. That's boron. And the reason why I'm drawing this out here, I'm drawing this example out here, is that this same process, this same sort of logical sequence can also happen with aluminum, which is one element down from boron. It's in the same group, and this is because it has the same valence electron set up in the orbitals. Because as we know, all elements down a group have the same number of valence electrons, and by extension have the same orientation of these electrons. So if we have this here, this is the valence electron configuration of aluminum, or aluminium if we were in other countries that I'm not in. I'm in Canada, and maybe Canada says it this way, I don't know, but I don't say it that way. I am maybe Americanized or something. Okay, so this electron, as we know, can also be promoted here. And as we know, this promotion for both boron and aluminum creates a hybridized orbital of sp2. sp2, we know one s orbital combined with 2 p orbitals, and they are half-filled. And this is why boron and aluminum bond in much the same way. Boron can bond stably with Bf3, and aluminum can bond stably with Cl, AlCl3. They bond in the exact same way because both of these are halogens. They both need 1 electron to bond with a half-filled orbital, and they both have 3 half-filled orbitals, 3 half-filled hybrid orbitals that are of the same energy to create molecular orbitals that are of lower energy than either of the hybrid orbitals, than any of the hybrid orbitals. In fact, if we're talking about semantics here, we always want to use the right words for everything, because that is how we communicate through language. Okay. And so see how they have the exact same molecular geometry. They both have angles that are 120 degrees, and they both form trigonal planar geometries. Trigonal planar. Okay, so now that we've established exactly how hybridization affects the bonding behaviors of different elements and groups, we are going to explore more in the next video exactly how this theory can be used to explain all molecules, to explain delocalization, to explain all of those exceptions and crazy things that we talked about in the last couple of videos. So I'll see you later, guys.